Section 4.5 sort of breaks down to two big chunks. The first chunk is how to perform a hypothesis test using a confidence interval. And then the second half of Section 4.5 is essentially a grab bag of things that had to fit into Chapter 4 somewhere. At this point, we've had two kinds of distributions that are generated by simulation. We had bootstrap distributions in Chapter 3, and we had randomization distributions in Chapter 4. The main difference between the two is that the randomization distributions would have an extra assumption, whatever is there in the null hypothesis. If you look at any of the three rows there, that's essentially what the difference is. In this example, we're going to construct a bootstrap distribution and a randomization distribution, and then line up how they relate to each other. This is going to be for a difference of means. Certainly we have quantitative data, two groups. And here's a bootstrap distribution based on that original sample, and 95% confidence intervals displayed using percentiles. This is all stuff that we had in Chapter 3. Now suppose if instead of a confidence interval, we wanted to do a hypothesis test. Instead of a bootstrap distribution, we're going to have a randomization distribution. From the sample data, the difference of sample means is 13.06. If we're looking for evidence of a difference, then the alternative would be mu sub a is not equal to mu sub n. The null would be that mu sub a equals mu sub n, or mu sub a minus mu sub n equals 0. So the randomization distribution should be centered at 0, and the way that you can get there from the bootstrap distribution would be to subtract 13.06 from each bootstrap sample mean. That way you go from a distribution of simulated samples that's centered at 13.06 to a distribution of simulated samples that's centered at 0. There's the randomization distribution with the p-value displayed. This would be a two-sided alternative, so two tails checked in the upper left, and the difference of sample means was 13.06, so that's the cutoff in the right tail, and it looks like we're getting a p-value of 0. Other than where they're centered, the bootstrap distribution and the randomization distribution are the same, except for random variation due to the way that the samples are generated. The only real difference is that the bootstrap distribution is centered at 13.06 and the randomization distribution is centered at 0. With the randomization distribution, we got a p-value of 0, so we'd reject the null at any significance level, really, but specifically at significance level alpha equal to 0.05. Earlier, we had the confidence interval, the 95% confidence interval using percentiles. The whole interval is well above 0. The left endpoint was 11 point something, which is certainly above 0. And this is the general idea of how you can do a hypothesis test using a confidence interval. Think about it this way. The confidence interval is supposed to provide you with a range of plausible values for the parameter. If the value that's in the null hypothesis is outside the confidence interval, then it's not a plausible value, so you should reject it. If that value is inside the confidence interval, then it is a plausible value, so then you don't want to reject it. That's essentially what this says. It's just a little more specific with the confidence level and alpha being specified. Notice that they match up. 95% goes with the alpha of 0.05, like how 95 plus 5 is 100. That's not an accident. That's the way that this works. So for other confidence levels, you'd have to adjust the alpha so that that relationship holds up. But that's basically the idea. The way that you can do a two-tailed hypothesis test, so one with a not equal to in the alternative hypothesis, is essentially you would reject the null if the value in the null hypothesis is outside the interval. This is what you do if you have a different confidence level. For 90% confidence, you need to use alpha of 0.1. 99% confidence, you use alpha of 0.01. In both cases, notice the way they add up. For the first one, 90 plus 10 adds up to 100, or 0.9 plus 0.1 adds up to 1, if you want to think about it that way. The alpha and the confidence level always have to match up correctly. I said this earlier, but here it is again. This is really how this works. The confidence interval contains a range of plausible values for the parameter. So if the value in the null hypothesis is not in the interval, then it's not a plausible value, so you should throw it out. You should reject it. If that value is inside the interval, then it's a plausible value, so you don't want to throw it away. So that's where you wouldn't reject the null hypothesis. In this example, we're going to do the hypothesis test using a confidence interval. At the beginning, we have our sample data, the 46%. That's effectively our p-hat, sample size of 300. And judging by what's in that second paragraph, we're looking for evidence that the percentage or proportion of American families owning stock or stock funds has changed. So changed, no specified direction, you need the two-sided alternative. And so if the alternative is that P is something other than 0.53 that's changed, the null would be that P equals 0.53. So here's a confidence interval based on that sample proportion. This is going back to the way that we would do things in Chapter 3. Confidence interval for a single proportion, you put in the numerator and denominator of the sample proportion, and then I just use the percentile, so 2 tail in the upper left, and then 0.95 for 95% confidence. There's the interval from 0.407 to 0.517. For our purposes, the important thing is that the value in the null hypothesis, 0.53, is not in there. So this is what we've got. The 95% confidence interval is from 0.407 to 0.517. 0.53 is not in the confidence interval that's larger than 0.517. So since 0.53 is not in there, it's not a plausible value for P, so we're going to reject the null at the significance level that matches up with our confidence level. Since it was 95% confidence, we're going to reject the null significance level alpha equal to 0.05. Then the formal conclusion, there is sufficient evidence to conclude what's in the alternative. More specifically, there's sufficient evidence to conclude that the percentage or proportion of American families owning stock or stock funds has changed. As far as a preference on whether it would be better to use a confidence interval or a p-value to come up with a conclusion for a hypothesis test, it depends on if there's anything else that you want. If you also want to be able to estimate a parameter, you need a confidence interval for that. But if you want to see how much evidence you have against a null hypothesis, you're going to need a p-value, since there's no way to do a direct conversion from one to the other. If all you're trying to do is make a decision about the null hypothesis, either of them will work fine. You'll get the same conclusion either way. Statistical significance we've had. You have a statistically significant result when what you're getting out of the sample is very unlikely to happen by chance if the null hypothesis is true. That's a thing we can quantify. That's what the p-value does. There isn't a way to quantify practical significance. The idea there is that you would have a practically significant result if the difference was large enough to matter to somebody. This is where these things might diverge in these first two bullet points. If you have a small sample size, you could have a big effect or a big difference, but that might not be significant because with a small sample size, you get a lot of noise, you get a lot of variability there. The other side of that is if you have a very large sample, a little effect might come back as statistically significant. The blue point is the important one here, that statistical and practical significance aren't the same thing. You can have one without the other, and where this tends to come up most often is with large sample sizes, where you get a tiny difference that comes back statistically significant, but it's something so small that it wouldn't affect anyone's behavior. For example, something like this. The sample size is huge, 10,000 people. That's a lot. And a difference in average weight loss of only 0.13 pounds. Now suppose the experiment lasts for a year. That difference is not going to be practically significant. 0.13 of a pound over the span of a year, that's really tiny over that time span. So this is what I mean, where you can have something that's statistically significant but not practically significant. And the thing that drives that is if you have a gigantic sample, which is what's going on here. Multiple testing. The issue here really is that if you do a whole bunch of tests, then they're all going to be independent of each other. So the probability of making a type 1 error ends up being additive. If you were going to do 2 tests instead of 1, but both of them were going to have alpha equal to 0.05, the chance of making a type 1 error is 0.1. It's 0.05 for the first test, plus another 0.05 for the second one. So you can see how this snowballs. In a study to determine if eating certain foods is associated with gender of a baby, researchers asked pregnant women about their eating habits, and basically what they ended up with was a questionnaire where you had to answer yes or no to 133 different foods. What they would have ended up with was 133 tests for a difference of proportions. If alpha was 0.05 for every test, then if all of the null hypotheses were true, so none of the foods had any effect on what gender the baby would be, you'd expect 6.65 tests to come back with a significant result. There was a significant difference found for breakfast cereal, but this might just be explained by random chance. We know that several tests are expected to be statistically significant, even if there are no differences. Even if all of the null hypotheses are true, we still expect to get a handful of statistically significant results. There is a way that you can adjust for this. The easiest one is the thing that I have in parentheses, Bone-Ferroni's correction. This isn't technically part of the course, but for completeness' sake, I wanted to mention it. With the foods and the gender of the baby, there were 133 tests. Basically what Bone-Ferroni's correction is, you take the alpha that you want to use and you divide by the number of tests. So instead of using alpha equal to 0.05 for every test, you'd use 0.05 divided by 133. Then that way, when you add all the individual probabilities of a type 1 error up, you'll get the 0.05 back. That's the easiest adjustment. There are ones that are better and more complicated, but that is one way of doing it. Publication bias can also be a problem because usually only the significant results get published. The way to counteract this would be making sure that a result is repeatable. Let's say somebody gets a significant result and then there are 20 repetitions of that experiment and they never get it again. That's one that's not repeatable, where you'd say, okay, that looks like it's a fluke, that first one. But what if someone gets a significant result, they do 20 repetitions of that experiment, and 16 times they get a significant result? There you'd say, okay, this looks legitimate because this keeps happening. So there is a way to counteract this. Not every publication is going to be that rigorous, and there are some things that you just can't repeat. So that would come into play too, but that would be the best way to counteract publication bias.